Okay, so so today is our 5th lecture in terms of lecture numbers. So we are still in the revision of MOSFET amplifiers. Now you may have got some announcements. So from tomorrow, the university is closed until 30th. So you'll be starting on 30th March, right? Now because we have 2 labs tomorrow, there's no point of doing 1 lab today. So I cancelled the lab. So we will resume the labs after 30th. So it's 31st March, we'll have labs and the lecture. Now that's if all the plans go as planned, right? So, okay, but that also means you get more time to do your design review one. Okay, so I put the assessment 2 details online. You may have seen it. So assessment 2, so are there any questions regarding assessment 2? If you have, just put it on the forum. I think it's best to get it clarified earlier. As I said, like now you won't have the assessment 2 obviously next week, the design review 1. So it will be like postponed accordingly. I'll update the timeline, the schedule on iLearn. So have a look at it. But you may also get a bit of extra time to work on the assessment 1. So if we have time after the lecture today, I will explain on assessment 1, assessment 2 a little bit more. And if you don't have time, I will do a separate video and then put it on echo. Okay? Now assessment 1 marking, I'm still doing it. So I'll probably finish my marking by the end of this week, and then you'll see those marks online in the grade books. Some of you may see some marks already because I'm marking few a day. That's how I'm proceeding. Okay, so let's go to the lecture today. So, and then if you have time, I'll talk about assessment 2. So MOSFET amplifiers. So we talked about transistors last week. So just recapping, the transistors, when we talk about VDS ID curves, VGS ID curves, and then transistor current equations for the VGS, right? So those are pretty much revision, and you're supposed to look at the Cedra Smith book or some of other materials to revise yourself. Now today we'll talk about more on amplifiers. So this is very critical, what we talk today, because you will be using it in the circuit design. Okay, so your design review 1, you will be doing your circuit design, and some of this content might be very useful for you to plan. So most transistor is a voltage control current source, as we said before. So it's a transconductance amplifier. Transconductance means it transforms a voltage into a current. So VGS here gets translated into the ID, and you have formula, the ID in terms of VGS in the saturation region, half muon Cox WOL VGS minus VTH squared, right? So you need to remember that. Okay, so what we are going to do now is we are trying to understand. So normally this is a simple amplifier. Okay, so if you in your designs you could be using an amplifier stage like this. Now this is a single stage amplifier because it only has 1 transistor. Okay. So this is also called common source. So you have the gate, you have the drain, you have the source. The source is grounded and there's nothing in here, and the gate is given a voltage, and based on that voltage there's a current that goes in the ID. Now because there's a current, there's a voltage drop across this resistor RD, we call this ID RD. So the voltage across that is ID RD, right? Now, usually we tend to get the amplified output from the drain terminal with respect to the ground. That's the output. Okay, and that output, you can find the voltage, which is the output, V output, as VDS, which is VDS equal to VDD, the total voltage, minus this voltage drop, minus IDRD, right? So that's quite straightforward. Now, using that, we can actually, we had different types of curves before, and this is a curve that we're going to call VTC, which is voltage transfer characteristics. Now, that will have two axes, VDS and VGS. So this is the VDS. In the previous transistor, the voltage between these two, how this changes with the gate source voltage. Now, there are three regions. First region, when the gate source voltage is less than threshold, you won't have any currents, right? So you will always have the VDD, the supply voltage, at the drain terminal as your voltage drop across the drain and source terminals. And when you don't have any currents, it's called the cutoff region, okay? Because it's below threshold. So that's a cutoff region. Then as you increase your gate source voltage larger than threshold, you will have your VDS start to drop, and then after a certain voltage, VGS, when VGS is greater than, so you remember the saturation region condition? So in your saturation region condition, ID VDS curve, you can have multiple curves for different VGSs, and in saturation region, what is your condition for drain source? VGS minus VTH, right? Now, so when VGS gets higher, when this gets higher, this terms increases, and at a point when it's actually higher than VDS, it starts to enter. When it's higher, you are in the triode region. So when VGS is higher, after a certain point, your VDS is smaller than VGS minus VTH. So you are in the triode region. Now, if in this course, basically as amplifiers, we will only use the saturation region because that's where we can get the most use. So if you want to use the transistor as a switch, we have to switch between the triode region and the cutoff region. We'll also talk about one example. So our region of interest is between A to B, right? So you can bias the circuit. When I say bias, I expect you to know the biasing, like just basic concepts of biasing because you covered it. You can bias it at any point in this region, okay? Now, these are the conditions, which is not very important as long as you know the main conditions, VGS and VDS, what needs to be done for each stage. Now, so we call this a cutoff region, and this is also cutoff. And in the triode region, you will get, do you get a certain ID current in the triode region? Do you get a current in the triode region? Yes, and it has a different formula basically, right? So you will still get some sort of a current, some sort of voltage, but it's not useful as amplifier. Now, so usually when you operate an amplifier, you need to bias it to a certain condition. This is all about DC biasing, right? So that's the DC voltages applying. We're talking about only DC at the moment. So the bias point, we call it quiescent point. So at the moment, let's say we pick a point like that. So what effectively we are doing in the circuit, so you have the taking output from here. Effectively, you will be having a signal on top of the DC signal. So example, if it's a microphone, okay, you'll be talking to that, okay, and then your signal will modulate the DC level, right? So you are simply changing the level of VGS on top of that. Now, based on your amplification, like your signal variation, let's say is a sinusoidal, you will also have a corresponding, so if it goes this way, your level out through here will come, so my time max is that way. So if I'm moving that, I'm moving down, right? So the gain of this circuit would be, so my signal changes here, say amplitude wise A1, and then here say A2. My voltage gain, which is AV, would be A2 divided by A1. So for an amplifier, it has to be larger than 1, because if it's the same, there's no point of having an amplifier, right? Now if it needs to be larger than 1, this curve needs to be more than 45 degrees, right? Because if it's exactly 45 degrees on same axes, depending on the same axes, well, you have to talk about the milliamps or microamps as well. But this curve, the gradient of that will give you that amplification. Okay, so we talked about that. So that's the, so depending on that, you can actually operate in multiple points in this curve between within saturation region. Which point gives you the maximum gain? Midpoint. And any other choices? So the curve is not linear, right? So this curve goes as, right? Now, if you are in midpoint, whatever you get here, so the curve, what happened, this curve has a drop like that. It's a, what is it called? Quadratic, inverse quadratic? And that tend to have the maximum slope towards the end. So if it has the maximum slope towards the end, that gives the maximum gain, right? So not the middle. But the problem with having the max, so what happens if you bias yourself at the bottom? What's the problem with that? Yeah, so you are in the saturation, you go to triode region, right? Sometimes. So if you go triode region, you don't get the amplification you want. But for maximum gain, you should be there. So you can be close to B, point B. I'm talking a few things in the next couple of slides in advance, but it's probably easier to illustrate like that. If you are in the B, and if you have a small signal variation, you can get a big amplification as long as a small signal doesn't go beyond that point B. So you could bias here and then still be within B region, not go to triode region. So there are different types of amplifiers. One called a high power amplifier. So high power amplifiers tend to operate towards the bottom, okay? Because you need to bias. So this gives you what voltage should you bias your circuit. So your VGS here could be, say this is 2 volt, and that's 0.7 volt. So you could bias at 1 volt, you could bias as 1.5 volt. When in your circuit, I'm talking about your design, depending on what point you bias, you will notice you can have different gains. So if you want to increase the gain, you can increase your VGS, right, in your circuit, right? So our spec for this assessment, I think, is 28 dB gain assessment 2, right? So let's say you bias it at 0.8 volt or 0.5 volt. I think the threshold for these circuits are 0.3. 0.5 volt and you don't get that right gain, one thing you can do is bias at a higher voltage, right? So you bump up your gain. Similarly, in your lab 2, when you tune the circuit, some of you couldn't get the gain above that 25 dB, right? So one thing you could have done is increase the bias voltage without tuning, and it just gives a bump, right? But the problem with that is, what's the problem if you increase the bias voltage? You have higher gain. It's not a problem. What is the drawback, I guess? So when you increase your VGS, you increase your ID, right? Yeah, so that drop increases, that's good. Now that's why you have the higher gain. But that means when you don't use a circuit, you still use that ID. That means when you're idling, because you still provide the bias, right? You are using more current, right? So more power usage pretty much, right? So what do you think your mobile phones or the watches or whatever it is, they have to have the lowest power consumption when they are not in use. So they tend to be biased at a very low voltage, VGS. So they might be biased here if they're not power amplifiers. I mean, obviously you won't have power amplifiers here. Only your transmitters in the phone, because you need to have a high power amplifier to transmit signal. In your receiving part, you have a low noise amplifier. That doesn't have to be high, high gain. It can be certain gain. You can have multiple stages, but it can be less current usage. So you bias it at a lower frequency. So that's the takeout from this. Okay, like that's what I want to give you. Like you may have learned this, but that's how you apply this in the when you design the circuit. Okay, so yeah, so this one I already talked about. Now, so this is what I've been talking before. So you have the gate source fixed voltage, then you give a varying voltage. So there's few notations that you need to go through. So I'll write them down. One term like simple V, capital GS, then we have capital V, capital GS, then we have simple V, simple GS. Okay, so depending on what I use, that gives you different meanings. Now, simple V, capital GS is equal to these two. Okay, now capital V, capital GS represent DC, right? So that's capital V, capital GS. Simple V, simple GS represent AC, and the combined it's a representation of simple V, capital GS. Okay, so if you have simple, letter plus some sub of capital, that means it's a AC plus a DC signal. Okay, just don't get this confused. Get that clear. I might not specify this later when I write, or even if I make a mistake, you should probably ask me whether that's the right one, because you can easily get that confused. Now what it simply says is that depending on your signal, okay, so this is what we talked about, you get a amplified signal. The other thing that is important here, what can you tell about the output signal with respect to the input signal? So there's obviously it's amplified. Other thing is it's inverted, right? Because when you increase that way, you go down this curve, right? So that's the increment in here, and that's a decrease in here. Okay, it's okay. It's just inverts, 180 degrees out of phase. That's all. Okay, but you tend to. It's easy for us to take the output. So what's wrong with taking the output from here to here? So it's not inverted. There's nothing wrong. It's much easier to take something with respect to the ground, because ground is everywhere on your board. Right, so that's why just a practice to get VDS with respect to the ground. Okay. So we had the formula VDS equals VDD minus ID RD, right? So we want to find the gain. So the gain, what we sort of derived was AV was delta VDS over delta VGS, right? So you should be able to derive the gain out of this. So you simply have to differentiate this formula. You can remember the end result, but it's because it's easy, I'll just do it here anyway. So if you do dVDS by dVGS, what you get, this is constant, goes away, and half Kn VGS minus VT squared RD, sorry, it's not 2 VT squared, it's 2 times, it's no superscript. So it turns out to be, it's minus half Kn VGS minus VT RD. Okay, so that's your gain. So this is something that you probably need to remember, but it's just amplifying the signal. So what it gives you, so let me write this a bit more clearly. So AV is minus, Kn is muon Cox WOL VGS minus VT squared RD. So now this tells you what you can do to increase your gain. So if you want to increase your gain, you can increase your mu n, you can increase your Cox. But as a designer, you don't have a control over that. So it's a process based. Depending on the process you use, the process will have a certain mu n Cox. Now in your case, for low noise amplifiers, you use gas. Now for GAN, like for power amplifiers, you use GAN because it has higher values, right? Okay, somehow a designer doesn't have control over that. The other thing the designer can do is control WOL. So WOL increasing, that would give you a higher gain, right? So if you use larger widths, so when you use 2 by 25 versus 2 by 50, 2 by 50 might give you a higher gain. But you also notice there was MCQ. Would it give you the larger gain overall, like over all the frequencies? No. When you plot it, it didn't work. So there might be other characteristics that come into play. Okay, but so you have to play with it. As a designer, you should know, okay, whether I should double my width. So when you use in your assessment, this is tips to your assessment. When you do your first schematic, designer one where you come up with your schematic, you let's say use 2 by 25 initially, then 2 by 25 in the second stage. Then you might say, I'm not having enough gain. Okay, I might have to use a 2 by 50 in the second stage, or 2 by 75 in the second stage. Okay, so likewise you need to make the decision. So you are intuitively using these things, but you don't know. So it's sort of putting a perspective to what this equation tells you. Okay, so the only outcome I want from here is you need to understand what this equation tells you. You don't need to remember, because your exams will be open book. If you don't remember, doesn't matter, you bring your book, that's fine, but you need to know the idea, what is expected, what are you trying to learn from this. Okay, so that's WOL. So what's the problem with having 2 by 25? So I have 2 by 25, 2 by 50. Then I say, okay, I don't have enough gain, I do 2 by 75. What's the problem with that? So again, more current. Larger your width, you can draw more currents, and then more currents not preferred. You want everything low power these days. Okay? So, okay, then we have VGS minus VT. Depending on your higher the VGS, you can get higher gain. Threshold, it's process based again. RD, so you can increase the RD. Okay? And then that way also you can change where you are, your gain. So you have few things that you can actually use to control the gain. So this is what we talked before, where you want the maximum gain. You probably very close to the point B. Okay, so this is so we have here VTC curve, and then we have ID VDS curve here. Okay. Now we want to map these points in here, A, Q, B, C, to the points on the ID VDS curve. Now before we map it, we also need to learn what is, well, you already have learned what's the load line. So ID VDS curve has the axis ID and VDS, right? So the previous the equation that you learned about VDS equals VDD minus IDRD, you rearrange that so that your one of the axis, y-axis is ID and the x-axis is VDS. So when you rearrange that, it will be in this format. Okay? Now when you have that, so this is your y-axis, this is your x-axis, sorry, this is your x-axis. And you will notice that has a negative coefficient, right? And then that's the gradient, and that's a gradient with a negative gradient, so that the curve will look like that, and the point where it hits the ID curve would be VDD over RD. So if you have higher RD, you will lower this curve, right? You'll go lower like that, okay? Okay, so that RD will control the slope of this. So each of these curves represent different points of your bias, gate source bias, right? Now, okay, let's get to something very simple here. Point A, your VGS is very low, right? Now that means you are almost below threshold. That means you won't have any ID current, will be very small. See, the VGS is here is equal 0, so you will be at this point, right? Okay, so the point B or point C, let's go to point C, that's easier. Your VGS is very large, that means you are actually at a higher curve, but your VDS is very low and your ID might be high. So you are somewhere here, okay? And the other points where you are just outside the saturation region, so where you enter the saturation region here, okay? Now if you bias your circuit for a power amplification, a higher gain, you might be biasing somewhere here. So your VGS, you might be switching between. So what happens when you modulate your gate voltage is you'll be switching between different curves, right? And then based on that, your ID will be changing. Yeah? So you will be switching between different curves, and ID will be changing, your VDS will be changing here. Okay? Now, for LNAs, most likely you will be biasing somewhere in here. That means you probably bias at a VGS lower, because so that means 0.5, 0.6, because you could go higher VGS, increase again, becomes bit one thing, it could become more noisier, so you have a noise figure to meet. Okay, so that might get a bit noisier. I'm not sure whether it will get noisier, it might. And you might also find it's hard to match sometimes. So slight changes. So this is the summary of what I've told before. Now, so I talked about we are using it as an amplifier, but we also we can use it as a switch. If you use it as a switch, so switch ideally would become an open circuit here, right? So if you use the transistor, so we want to open this, we have to be operating at point A, because if you open, so the point A represents ID equals 0, right? No current. It's like opening a switch. So if we can bias it so that its ID equals 0, that means your VGS is smaller than VTH. It is an open circuit, so it acts as a switch. So the benefit of the transistor is so we know it's a 4-terminal. We actually ground the bulk, which is a B terminal. Then we have one controlling two other major signal to go, and the one control. So when you control the VGS, you can configure it so that if you say the VGS to be lower than VTH, then it's open circuit. When you do it in the triode region, so you are close, just above VTH, but not in saturation, because the VDS condition doesn't satisfy. You make it operating as like it's turned on, right? It gives you a current. So that's how you can do it as a off or on. Now this is digital domain mainly. So we don't really do a lot of stuff on digital domain. So digital domain, what I meant was this is more analog electronics that we are talking, amplifications. But on and off is a NOT gate. You can just create a NOT gate. Now once you create a NOT gate, you can create any gate from that, right? So that's a basic building block. So as long as you know how to build a NOT gate from a transistor, then you can just put it as a base building block and then create your digital circuits. So we talked about locating the biasing point. That's just using different points. So we said usually we would tend to get here for the highest. So two considerations: required gain and signal swing. So you can get a higher gain but less swing. Now you would want in a low noise amplifier more swing as well. So you are biased somewhere in the middle just to be safe, okay? Because you don't need higher gain. So you can set your RD, depending on RD, that's given by 1 over RD. So depending on your RD, you could be, so for example, if you do Q2, you're close to the triode region, you don't have enough leg room. If you do this with a small RD, you don't have enough headroom because you will be reaching the triode region. So you tend to have your load line. You need to pick your RD carefully so that your load line in here stays somewhere in a VGS you want, and then still can swing between different lines. Okay, so I think now what we should learn, so we should revise on the transconductance or the gain. So something called transconductance. So we're going back to ID and VGS curves. So ID is given by DC current plus small ID, right? So that's a DC current and that's the AC current. Now for a GM is called the transconductance parameter. It's defined by how much current, how much ID change you get for a small VGS change. My notation is wrong, V capital GS. So for a VGS change that you do, how much current change do I get? So that sort of translate my voltage to a current, okay? So it is a relationship between current and the voltage. Why isn't it conductance, but it's called transconductance? Why is that? could be, someone could call it conductance. But we still call it transconductance. There's a reason for it. So, okay, let's say for a resistor, you have voltage across that, and then you have a current, and then resistance is VOI, right? So you are measuring the voltage in between those 2 points, right? But say there's a circuit that you can actually change the voltage by changing the current somewhere else. So you can't call it a resistance, we call it trans resistance, because you change the current somewhere else and the voltage changes. Okay, same way here we change the voltage VGS here, and your current ID changes. So that's why it's called transconductance. Normally I divided by V is conductance, but it's not between the same terminals, so we call it transconductance. Okay, now ID is given by half UN Cox WOL VGS minus VT squared, right, in the saturation region. So assuming you satisfy those conditions. So if you want to know the transconductance, you basically have to do okay. So that means when you do that, half 2 times so that gives you mu n Cox that's your GM. Yeah. So if you remember a few slides before, we worked out what is our gain, AV, right? So let's go back. So remember this, mu n Cox WOL. Okay, so what we got here, this part, so we should cancel actually 2, right? Because the half cancels out with 2. So we got basically AV equals minus whole GM RD. Yeah. So gain of the voltage is depending on the RD and the transconductance parameter. So we can find the transconductance parameter as long as you know our biasing VGS, then we can find the gain of the whole circuit. Okay. So that's the idea. So you might get a question in the exam. I'll do some sample questions to find this GM. So you have to know this equation. Obviously it's open book, so you can bring the books. You don't have to remember it. Okay. Somehow the GM can have different forms. So if you know mu n, okay, so let's look at GM a little bit more in detail. So I can also rearrange this formula. This one, ID, take the 2 here, divide by mu n. Oh, I don't even have divide. So I'm trying to leave mu n Cox WOL VGS minus VT. I take 1 VGS minus VT down here. So this term is basically that term. So GM can also be written as 2ID over VGS minus VT. Okay, that's another way of writing it. Or you can completely remove VGS minus VT. So if you want to remove VGS minus VT from this equation, you can get 2ID for this whole term. I just say Kn, just for so it's easier. Then I could square root. So that's VGS minus VT. and then I can sub in here gm equals 2id over kn square root times kn. So it gives me 2kn id. Okay, so that's different. So kn is 2 muon cox wol id. So there's mainly three ways that you can find GM depending on what you get. So to use, I'll make sure these slides are uploaded. So if you want to write, you can write, but it'll be there. And we have that in a slide in the next couple of, I think in the next or second or next slide or after. Okay, now there's a bit of confusing messages here. One, if you look at this formula, it says VGS minus VT is proportional to GM. Here it says inversely proportional to GM. So what's right? Oh, what's that? Why is that? So the two equations give you two different meanings. So the one GM is proportional, one.
Because in the second formula, we still have ID.
Yeah.
Depend on the VGS minus VT.
Yeah, that's right. So ID itself is dependent on VGS minus VT. So you can't really interpret the second formula as inversely proportional. And also you need to remember when VGS minus VT, you need to make sure other parameters are fixed. So if you do VGS minus VT, this is inversely proportional, that's true. But if your ID is fixed. Okay, so that's why so the equations are fine. So for example, you get a question, let's say a circuit is given, you have the ID current, and VGS and VGS is given. The easiest way to find GM is just use the second formula because you don't have to do any of these because ID is given, VGS and VT is given. Okay. Right. So this is all, like you should have covered this in the 3Os ELEC4076 or whatever similar courses that you've done. This is simply okay. So that what I've talked about before. These are the equations in a slightly different format, but that's same as that. Okay, so we talked about this in a briefly before. When we calculated, so any of these circuits, I said there's a DC part and there's a AC part. Now, if you have an AC part, you should be able to divide this circuit into two different level. We call it large signal and small signal, which you might remember this. So I try to isolate the DC because DC is fixed, right? And then I try to just focus on the AC signal. Then we call it the small signal model. But the small signal is when you apply small variations to your DC biasing point. If you apply large variations, so for example, someone has a high amplitude voice and then talk to this microphone, goes like crazy. This model won't work. Okay, you have to be gently speaking. Model might work. So just an example. So you can divide this whole circuit to two areas, and then just remove all the DC part. Just analyze the small signal AC part. Okay. Now there's a way that you do it. I'm not going to go in detail because if you can't remember, have a look at the book or videos on this course. There's a lot of videos on this. There's a few steps that you follow to derive the small signal equivalent circuit. So I'll do one example. So you guys might remember when I do it. Okay, so I'll do the example here. So this is important. The small signal model just represent only the AC signals, right? Now we want to. You can write, your equations. VDS is equals to VDD minus IDRD, and then you can solve So if you want the gain, you can, once you solve, you get GMRD, and then you find GM, and then you find the gain. You can do it that way. But it can be like when you have 2 transistors or 3 transistors, it gets very hard to solve these equations. Say, for example, you have another transistor in parallel to that, okay, and then they both share the same output. It gets confusing, and I mean, you can still work it out. It gets more linear equations, more algebra. What is easier is to come up with the equivalent circuit model, so that you can look at, okay, these are parallel, I can just simplify it, things like that. And that's why we come up with a equivalent model for the small signal circuits. Now, equivalent model is very simple. You have a gate terminal, you have a source terminal, drain terminal, then you have a voltage controlled current source. See, the voltage is VGS. It's open because gate and source, there's a cap, that's a cap, right? And then, so it's an open circuit, the voltage controlled current source. The relationship between the VGS and the current that goes in here is through transconductance, which is GM, right? So it's GM VGS. The current that goes here is GM VGS, depending on what you said. So that's the model that we use. Usually they have a finite resistance. That's at the drain terminal, and that's why you also get, you know, that sort of behavior. That R0 is usually high. So we also have an output resistance, which we denote as R0. For a question, you might be given what is R0. So only thing you need to find is GM from equation. So you can use the GM formulas that we talked about, GM, one of those 3, to find GM, and then use that to find the current, because you already know VGS. Now, okay, we'll try to do one equation. So if I want to represent this circuit here with a small signal model, I can replace this with the model that I was talking. So G and the source, and then you have a current source, GM VGS, and then you have an output resistance R0, right? So that's a drain terminal. So that drain, gate, and source. And then in the small signal model simplifications, the capacitors. So are we talking about AC signals or DC signals in small signals? AC, right? So AC signals, when you have a capacitor is like an open circuit for DC signals. So that's why you use a capacitor here. But for AC signals, you know, the impedance of a capacitor is given by 1 over J omega C, right? Yeah? So that's the impedance of a capacitor. Now what does it mean when you have higher frequencies? This term becomes smaller. So if it's smaller, that means low impedance. So for a higher frequency signals, capacitor look like a short circuit. Okay? So if you're working high enough, like say in gigahertz, so it's a short circuit. Maybe 50 hertz, it's not. Like, you know, your AC current, it might not. But for higher frequencies, it is. The same way, if you have an inductor here, J omega L, right? Inductance. So higher frequencies, this is high impedance. That means because it's high impedance, for higher frequencies, it's like an open circuit. For lower frequencies, that's a short circuit. Okay, so that's a trick that we use when you work. So we want to separate DC from AC, you can use caps. So for a DC, it's an open circuit. For a AC, this is a short circuit. And that's why in the small signal model, when you draw the equivalent circuit model, these caps, you replace them by a short. Okay? I guess you guys remember from that, that from the previous courses. But if not, just all the caps for higher AC signals, we can short them. Okay? So now that means your V1, there's no cap shorted. So that's your input. Then your VDD, all the DC sources, we short them too. Because we separate AC and DC. So DC VDD is already taken into account. So the AC wise, it becomes a ground terminal, right? So you have RD connected to the ground. And then you also have a short cap, and then RL connected to the ground, and then you take your output from here. Okay? Is that clear? So what you get, so this is connected to the ground, so I can simplify this. This end RO, RL, RD. I'm getting the VO output from here. Right, I'm just drawing this part. So your VGS is pretty much V1, right? Because there's nothing in here. So what's the current that comes in here? So this whole thing it's 3 resistors in parallel, so you can just do one circuit. So the current that comes here is GM, VGS is V1, right? So what are we trying to find here? We are trying to find the gain. So gain means voltage gain, AV, V out versus V in. So I just want to find this for this circuit, okay? So I'm trying to solve this circuit so I can find AV. Now, so this looks like I get a current GM V1 here, okay? And that current, because it's open, will go through here, through this loop, right? So the voltage drop across, which is V out, is current goes here. So the voltage we measure it from here to here, so that's negative GM V1 R1, okay? So what we want to find is V out over V1. So if I rearrange this, so that's my voltage gain. Okay, so that's the small signal voltage gain for this circuit. Okay, so we did it for a circuit that's much simpler. So you can do the same thing as an exercise, and I think it's already shown how to simplify it. Then you can work out what is the AV of this circuit, small signal gain. Okay, so you pretty much have to follow your KCL, KVL, and then simplify the circuit, and then find a relationship between output compared to the input. Okay. Now the last point is different ways of biasing. So in this course we focus more on common source. The common source is where your gate is supplied with the input, your drain is with the supply, your source is always grounded. That's the source is shared between the output and the input, and that's the common source configuration. Okay, and that's what normally gives you the best biasing conditions, biasing configuration for amplifiers. Okay, so we have other circuits.